Hey everyone, just wanted to run through another one of the kind of problems that we did in class, or another two of the type of problems that we did in class, so you can hear me explain how things work and why things are going the way they're going, etc., etc., etc. This problem comes from this problem set, which I gave to you on Monday, I believe, the equilibrium in 2D problem set, and it's number 8. The problem says, three customers at a boutique are fighting over the same prom dress. They apply forces as indicated in the figure below. Technically it's to the right, but you get the picture. So part A says find the magnitude and direction of the net force on the dress. And part B says find the magnitude and direction of the force that the sales clerk needs to apply to keep the dress at rest, which will keep it from ripping in theory, blah, blah, blah. Yeah. Let's handle part A first. So the first thing I'm going to do is I'm going to recreate this picture down here. There's my x-axis. There's my y-axis. Okay. Three forces. There's a 200 Newton force, which I will use green for. 200 Newton force comes along like this. Then the 300 Newton force I'll represent in red, like this in the picture. And then the 155 Newton force I'll use blue, and that looks something like this. So for part A, it says find the magnitude and direction of the net force on the dress. We talked about in yesterday's little video that the net force is just a fancy way of saying what is the resultant force. So we need to find the resultant force of these three non-perpendicular vectors. We talked about the idea that the way these vectors are set up right now, we can't find the resultant vector of these three because they're not set up tip to tail. So first thing I'm going to do is I'm going to take these arrows and make sure that they're drawn at the correct angles so my picture comes out the way that it's supposed to. Hopefully. Don't mind this. This is just me being a little, making sure I'm getting it all done right. So there's my 300, there's my 200, and then there's my 155. So we said that in order for to find the resultant vector, we need to have the vectors set up tip to tail. So they have to, the next one has to end where the previous one, or sorry, the next one has to start where the previous one ends. In this case, there's actually three of them. So I'm going to take the red and I'm going to move it to the end of the green. And then I'm going to take the blue and I'm going to move it to the end of the red. I've set these vectors up tip to tail. Now the resultant vector looks something like this, represented by the purple. The vector that we draw from the beginning of the first to the end of the second. Or sorry, to the end of the last. In this case, it happens to be the third one. Now, process of finding the resultant vector. All of these vectors, blue, red, green, that are not currently on the x-axis or y-axis need to be split up into components. So each one of these three vectors has a horizontal component and a vertical component. And then this red one also has a horizontal component and a vertical component. This blue one also has a horizontal component and a vertical component. Okay? Now, they look kind of weird because of the way that I originally moved the vectors, but what I'm going to do is I'll take this, see if I can work this and get these three together. Maybe not, but anyway, if I go here, here, and here, right, and then I go here, here, and here, that might look a little bit more conventional as far as what we've been doing. Okay? So on these three triangles, you know the hypotenuse, which is the amount of force. You know one of the angles, so you can use sine and cosine to find the rest of the sides. I'll give you a second to do that or hit pause. What I'm going to do, the answers to this problem are already posted online. So what I'm going to do is I'm going to go to the answers like this, and then I'm going to show you these three individual triangles. There's the components of all three of those triangles written out. So we said the next thing that we have to do, going back to this original picture, is we need to add up all the x's and add up all the y's. Now if you notice in this case here, on the x-axis, there's a horizontal one that points to the left, there's the red dotted horizontal one that points to the left, and then there's the green dotted horizontal one, but it points to the right. So you got to do the appropriate math steps to make sure you're adding and subtracting. On the verticals, you have one green this way, up, red dotted up, blue dotted down. Once again, do the appropriate math techniques, or do the appropriate math operations, plus, minus, and you end up finding what's left over on each axis. And when you find out what's left over on each axis, it should look like this. So this is what's left over on each axis. Now you have a right triangle. Guess what this double dotted line here, that double dotted line, let's see how well I drew my picture. If I cut this and bring it over here and paste it, not too bad. Not too bad as far as what the resultant is. Remember that purple vector is the one that I drew originally when I set up the blue or the green, the red, and the blue tip to tail. That was the vector I drew from the beginning of the first to the end of the last. Now it's just a matter of doing Pythagorean theorem, using your tangent function to find the angle. And when you do, you should end up with this. So here's your rounded answer, sig digs. Now, for the second part of this problem, remember there's two parts to this problem. For the second part of the problem, it says, find the magnitude and direction of the force that will keep the dress at rest. We talked about the idea that at rest is another example of equilibrium. So for part B, we just need to take the answers here, and we know that in order to have equilibrium, you have to have a force on the x-axis balancing out what was remaining on the x-axis from those three original forces. You need to have a force on the y-axis balancing out what was left of those three original forces. And then, if you set those up tip to tail, you can find yourself that force that would produce equilibrium. Didn't draw them exactly the same, but you get the gist. Okay? When you do that, you should end up with a number that's very, very similar to your answer from before. Also an angle that's very, very similar. But when we do that, let's go back here. Let's paste that here. Sorry if this is making you a little dizzy. It's going to look something like that. And there it is. So once again, that answer, similar numerically to what we got from the answer that's the resultant vector, but angle's a little different. So there's number 8. Another problem that I had you do, or that I wanted you to do in class from the problem set that was similar to the second problem that we did in class, incorporating gravity, was number 2. So number 2 says, a 10-kilogram mailbag is suspended by 2 cables. One cable is completely horizontal, and one cable makes a 37-degree angle with the ceiling. If the bag is not moving, what is the tension in each cable? So first thing I'm going to do is I'm going to draw myself a room. And there's my room. Next thing I'm going to draw myself a mailbag. Here's my mailbag. So it says that it's suspended by 2 cables. One cable is completely horizontal. There it is. And it says the other cable makes a 37-degree angle with the ceiling. So that means that this angle right here, forgive me for my writing, I'm using a mouse and not the pen, is 37 degrees. So we said that there are three forces, and he says if the bag is not moving, what is the tension in each cable? If the bag is not moving, that's a tip-off of equilibrium. So we have to have equilibrium x-axis and y-axis in this problem again. Very similar to the problem that we did in class. There are three forces acting on this mailbag. The first force is the force of gravity. That force of gravity acts straight down. And based on what we've done up until this point, I'm going to make it a little shorter just for a little more consistency. Based on what we've done at this point, we know that the force of gravity acting on something is equal to m times g, right? The mass of that object times the force or the acceleration of gravity. 9.81 times 10 gives you 98.1. So that's how many newtons there are, that force going downward. Then there are two other forces. One is the horizontal cable. I shouldn't have done that. One is the horizontal cable. I'll use blue to represent that one. That goes this way. It pulls horizontally. The other one is the cable attached to the ceiling. It pulls in this direction. Over there. If we take a look at this picture, right, even though I drew the room the way that it is, here's my x-axis, and here's my y-axis. Okay? If we take a look, the red vector is not on the x-axis or the y-axis. So by now, you should be getting the message that when we have a vector that's not on the x or the y-axis, you know that it has components. It has a horizontal component, it has a vertical component. In this case, because the bag is not moving, that means that this object is in equilibrium. And if it's in equilibrium, it's got to have equilibrium on the x-axis and the y-axis. In this picture, there are only two forces on the the y-axis. There's the green force of gravity pulling downward. There's the upwards force from the y component or the vertical component of that cable. So if there's only two forces and they have to add up to 0, if the downward pull of gravity is 98.1, that means that the upward component of that cable has to be 98.1. Now we have a triangle where we know one of the sides and we know one of the angles. Even though it gave us this angle, which is 37, we can adjust some things if we want to and slide the components this way, and now that 37 is within the triangle. That 98 still comes along like this. So now you have a side and an angle. You can use your trig functions and you can find out that, let me grab this here. You can find out that using your trig functions, okay, that in this one I called this tension 2, that the red cable should have a tension of 163 newtons. In this case, I'd use my sine function to find out what the hypotenuse is. Now, on the other hand, we know that we also have to be balanced on the x-axis, and that means that there's only two forces on the x-axis. This blue one here and this dotted red. They have to balance each other out. So now I have a triangle where I know one of the sides and the angle. I can find either of the other two sides. I found the hypotenuse. It turns out to be 163. But I can also find the x component. And that horizontal component is 130.18. And that means that if the x component of this triangle is 130.18, then that also means the horizontal cable has to be 130.18 as well to balance out on the x-axis.